Okay, we continue our graphing unit. We're now going to talk about how to graph an ellipse. Ellipses have a lot of similarities to circles. This will correspond to assignment number 24. I think it would be helpful for me to first of all, let's put up the fact that this is going to be example number 1, all right? And I think it's helpful to talk about the fact that ellipses are very similar to circles with one major difference. But an ellipse has a center point, which we will discuss how to discover the center from that equation. And after we plot that center over here, then we'll talk about the fact that with an ellipse, instead of traveling the same distance in all 4 directions like we did on a circle, R, radius, left, right, up, down, on an ellipse, we travel a certain distance to the left and to the right, which we're going to call A, and we get these 2 points out here, all right, horizontally. And then vertically, we travel a different amount, which will be called B. So with an ellipse, we go A to the left and right, B up and down. And so instead of being the same distance in all 4 directions, instead of being a perfectly round circle, it would be an ellipse. So that's the general thought process. So let's go to the notes and talk about ellipses here. So an ellipse has a standard format just like any other. We've had equations of lines and parabolas and circles. They all have their standard format. Our desire is to have the equation look like this. X minus h squared over a squared plus, and you see it there. This first example resembles that very nicely. Quantity squared, fraction plus fraction, 1 equals 1. These first couple of examples, it's in the perfect format. So, if we were to identify the center from this, I hope you would remember how you find the center from a circle. You have your notes in front of you. The x-coordinate is the number that's in there being subtracted from x, and the y-coordinate is the number being subtracted from y. You also might remember that we said, what would you have to put in for x to make that equal 0? And you would say 5. This is just like the identification of a center on a circle. And then what would y have to be for that to equal 0? That would have to be negative 3. So again, this is x minus 5, this is y minus negative 3. That's the same identification as it was on a circle. So the center of this ellipse would be the ordered pair 5, negative 3. So on the graph paper, 1, 2, 3, 4, 5. 1, 2, 3. There we go. There's our center. And everything will work outward from there. That's our general picture of an ellipse. Here's the specifics on this particular one. So how do you find the center of an ellipse? The same way you find the center of a circle. The h and the k. All right. What are the values of a and b? Well, we're going to get axes, and as I mentioned on my general picture, plus or minus a units horizontally, plus a this way, minus a this way, horizontally, and b vertically. Plus b up, minus b down. If you look at the general format of this, the value of a mentioned here, as well as on my picture, is this denominator of the x. So the point would be in this particular question, a squared would equal 9, wouldn't it? See how the a squared is the denominator of the fraction that has x in it? And by the way, I always point out to people that the x-axis is the horizontal axis, so this a value is going to be the horizontal. And if you solve that for a, the square root of 9 is plus or minus 3. And here's the visual. Plus 3, we're going to go 3 units to the right of the center to get a point on the ellipse, and we'll go minus 3. So plus or minus 3. So from this center point, we're going to count 3 boxes to the right, 1, 2, 3. And what I like to do there is notice that that would land out there on the 8 on the x-axis. And as we plot these, I suggest that we label them. So with that ordered pair, if we go 3 units to the right of our center, be the ordered pair 8, negative 3, and this will be useful information later on. That's the ordered pair there. That's an actual point on the ellipse. And there's your blue plus A, all right? Minus 3, so we go back 3 boxes this way. Start here at 5 and go 1, 2, 3. Wouldn't that land at -2 here? Isn't that 3 units this way on the x-axis? So that ordered pair, it appears, would be, not -2, sorry, 2, -3. 2, -3 would be that ordered pair. 2, -3. And that'll be to the right. So 3 to the right, 3, I said to the right. Here we go. 3 to the right, 3 to the left. That's called the horizontal shift. Horizontal shift. How far you travel to the right and to the left from your center. And again, X, horizontal, horizontal. All right, similarly, the vertical shift, how much you go up and down, B. So in this question, B squared is 25. Look at the standard form of this. B squared is the denominator of the y fraction, let's call it. And y is vertical, so B is vertical. Y is vertical, B is vertical. Solve that, and that will be plus or minus 5, won't it? So we're going to travel from the center, 5 up and plot a point, 5 down and plot a point. So it's counting boxes, isn't it? So if you start at the center and you go up 5 units, and remember we're at -3 here, so if you go up 5 units, 1, 2, 3, 4, 5, and then 5 up from here, right? So that ordered pair, it looks like, would be the ordered pair 5, 2. That's 5 units upward from the center. And that gives you another point. And then similarly, we'll go 5 units downward, minus 5 in other words. So we go back to the center and we go 5 units down from the center, right? So look where the center is over here on the y-axis. 1, 2, 3, 4, 5. Wouldn't that be 8 units down here at -8? Over here we count 5. 1, 2, 3, 4, 5. Plot our point. Looks to me like that ordered pair would be the ordered pair x5, y -8. And that's 5 units below the center. And then from here, we can simply sketch our ellipse. And there we go. All right? So, there's that. Now, what are these other boxes? What are vertices? What are co-vertices? Well, you're going to get a major axis. All right? And by definition, one of these is going to be longer than the other. A and B are going to be different numbers. If they were the same number, it would have been a circle. All right? So the major axis, the one that's longer, is going to be what are called your vertices. So you look at this and you go, well, let's see, that's 3 units each way. This is 5 units each way. It looks like the up and down one would be the major one, the longer one. And so these endpoints, the 5, 2, and the 5, -8, since they're the endpoints of that longer axis, they would be our vertices in this particular case. So the ordered pair 5, 2 is one of our vertices, and the ordered pair 5, -8 is the other. So it's all a matter, the word vertices should make you think which one's longer. And it could be either one, okay? It could be the ones on the side. But on this one, 5, a vertical shift of 5 is longer than a vertical shift of 3. So, those are the vertices. On the other hand, you have a minor axis. That's the one that's shorter, and its endpoints are called co-vertices. So similarly, this is the shorter one, right? The blue one in this example. So with these endpoints, which are the 2, -3, now you see why I wanted you to label them on your picture. So 2, -3, as well as 8, -3, would be our co-vertices. That's it, all right? I hope that made total sense. We could talk a lot about more stuff. I could ask you to identify what are called the foci. I have decided not to, so don't worry about foci. There is a formula for finding them. Time is of the essence. It's not necessarily required. It would be awesome to talk about foci, but I've made the executive decision not to worry about them. So center, vertices, co-vertices. So vertices. There's your vertices. done dirt cheap.
Vertices, done dirt cheap. Vertices, done dirt cheap. Vertices, done dirt cheap. Vertices, and they're done dirt cheap. Vertices, and they're done dirt cheap.
That was an abrupt ending, wasn't it? All right, so there would be your song for Vertices, done dirt cheap. Ask your parents, your grandparents, AC/DC. You know, years ago, so I've had that link for Vertices done dirt cheap for quite a long time here. For years, I did not have one for co-vertices. You'll notice there is one now. There was a gentleman who sat right over there. His name was Kirk, as a matter of fact. I remember him very well. Hi, Kirk. How you doing, Kirk? And Kirk said to me one day, he goes, you got a link for co-vertices? And at that time, I did not. And I said, I'm sorry, Kirk, I don't. And a week later, Kirk came back, and he had some lyrics for co-vertices. I asked him if he would sing it, and he decided he did not want to do that. So, this is a collaboration of Kirk's wonderful lyrics and my less than wonderful singing talent. So ladies and gentlemen, here would be your song for co-vertices.
Co-vertices, co-vertices, out from the center but not as far as the vertices. Graphing ellipse, so hold the dips. Teacher equips, so get a grip. On minor axis, that's what the fax is. Co-vertices.
Well, thank you, Kirk. Of course, everybody recognizes that as being from everybody's favorite, The Little Math Maid. Wah, wah. I miss you guys.